Let's go into the topic because this is really the most interesting part of this webinar. Let's start high level. What is the challenge with N2O? Okay, well, I was at the Singapore International Water Week a couple of weeks ago, and there were two big topics. Actually, if you summarize this whole event, digital and greenhouse gas emissions. And these two, well, these two combined is actually the topic of this webinar. But actually operating a wastewater treatment plant or designing a wastewater treatment plant in 2022 is way more complex than it was in the past. Why? Because you have to balance all these goals. The first one is your effluent quality. A plant is there to treat wastewater, right? And it started with carbon. Now we have nitrogen, we have phosphorus, and now we are even talking about micropollutants, in some cases in reuse purpose or in Europe for the removal of them. So this is already a challenge on its own. You have to balance it with costs. And now we have this third dimension of N2O or climate impact. These three conflict. Not a single plant in the world is a perfect plant with all of them in balance. So the cheapest treatment for limited climate and the best effluent quality, it doesn't exist. You really have to balance it. And this makes operating a wastewater treatment plant today a bit more complex, and it makes it a balancing act. So why is N2O important? Well, I should not probably introduce this. That N2O is approximately 3,000 times bigger, let's say, when it comes to climate impact compared to CO2. So yeah, this delivers some interesting key figures. Well, wastewater treatment, approximately, if you look at the global carbon emissions, it accounts for 3% of that. If you only look at N2O, it is a big fraction of this. And in fact, N2O, yeah, they account, including the drinking water and reuse industry, it accounts for almost 30% of the industry emissions. So it's a big issue, right? If we want to lower our footprint. N2O can increase the wastewater treatment carbon footprint with almost 80%, with up to 80%. So there are several papers on that. Where is it coming from? I think most of you also are familiar with it. It's coming from the biology mainly. There are a couple of other sources, but anoxic zones, aerobic zones, biological nutrient removal. What are the questions then? Huh? If you go back to this poll, what are the main questions in the markets? We have broken it down in two big parts. A first one is, how good or how bad are we doing? How severe is the N2O problem? That's assessment. Once you have done an assessment, you can mitigate. What are the questions with assessment? Well, how is the N2O emission at my plants? Which ones are the hotspots? How do I actually prioritize? And how do I adequately do an assessment of this N2O emission? Because it's very complex and it's not easy. Yeah? We will come back to that in this webinar. Very important questions. When you look at mitigation, well, what are the strategies on the market that exist to mitigate? Probably it's very plant specific. So because, yeah, so the question is, what is most effective for my plant? And how do I mitigate N2O without compromising effluent quality? Just remember this balancing act. And what are the generic learnings every utility or my utility can apply over and over again? Many questions we are looking for. A recent post by Water Care Services, which is a utility in New Zealand. Yeah, this is a post from last week on their LinkedIn channel. N2O is not a laughing matter, they said, right? But if you read a bit more in the post, it's all about the challenge. It's really, how do we get the answers? How do we adequately measure it? How do we find the questions we need? We were talking with a Dutch utility customer last week, and they said, yeah, we want to measure N2O in that transition zone, for example, a zone between an aerobic part and an anoxic part, but it was covered and inaccessible with a sensor. There are really many limitations and black boxes when it comes to N2O assessments. So with this introduction, I will give the floor to Ingmar. He will be introducing the N2O topic more.
Okay, thank you, Wim. So indeed, I will go a bit further on this topic where the nitrous oxide exactly is produced. So Wim already highlighted that. So you have different microorganisms that are doing different conversions. And usually it's actually under, let's say, extreme conditions. But what do I mean by that? When there's actually a metabolic imbalance. So for example, if you have high levels of oxygen or low levels of oxygen or high levels of nitrites or ammonia, that's typically when the pathways for N2O production are being triggered. And what we will show here is that actually this can happen and actually happens in most of the bioreactors. So when we look at that, what is then driving the N2O production? Well, you have several parts that have an impact on that. First of all, you have your influent that has a certain load, a certain quality, and a certain quantity, a certain flow rate, which is not fixed. It's varying in time. Then you also have the type of the reactor. Okay, you can have different types of reactors, different processes, and different process designs. Also, that will have a different impact on the N2O production. And then you have the operation, which is typically going to be, for example, set points of oxygen, etc., or cascade controllers, whatever. So all these things will have an impact on the amount of N2O that would be produced. So let's have a look at some evidence of this temporal variability. Okay, so what we see here are some pictures from two papers, and the references are shown below, where measurements of nitrous oxides were performed during the course of one day. And then you can clearly see, so N2O here is represented by the yellow symbols, that it's not constant in time, it's varying in time, and that it's related. But also you cannot really see very clear patterns. There are some patterns in there, but it's definitely not going to be completely fixed. So one thing that we want to also add to this, next to the temporal factor, is actually the spatial factor. We have seen that, or we talked about these metabolic imbalances by some extreme conditions. And actually the fact that a bioreactor is not a completely stirred tank reactor, as we will show later, you can have some of these extreme conditions even in locations where you don't expect it. So we believe that mixing is also a very important topic. So that brings us to a first key point of this webinar, that basically due to this complexity, it is really hard to assess and to effectively mitigate N2O emissions. So indeed, we have different factors that have an impact: the influent, the operation, the system type, and the mixing. So this also means that the assessment and the mitigation will also be highly plant dependent. Okay, with that, I will give it over to Usman.
Yeah, thank you, Ingmar. Indeed. So apart from all the other things, what Ingmar mentioned, one of the things was the mixing or the local gradients. So let us dig deeper a bit in the gradients in the bioreactor. We will start with a very simple example of a coffee cup where you are pouring milk in coffee, and you would expect that it will actually mix immediately. But you know that if you don't stir it very well, it takes much more time to actually completely mix. Which means the gradients, even at that small scale, exist. And by the gradients, we mean the difference between concentrations across the whole reactor system. What we did in order to confirm this, in 2017, we did a measurement campaign on a wastewater treatment facility in Netherlands, in Eindhoven, using a crane with multiple sensors attached to the crane, and we went deep into the reactor to measure dissolved oxygen and also other measurements. But if we go forward in the next slide, we will show how it looked like. So we attached several sensors with the crane, and we went deep inside the reactor, and not only deep, but we also measured across the whole width of the bioreactor. And we observed that actually dissolved oxygen is not really constant, but it's very varying, and it means that there are really gradients existing in such a big bioreactor as well, even though in the very much aerated zone where the aeration was really happening. So in this graph, there are two graphs which are two different locations in the bioreactor. On the left side, you see dissolved oxygen across the depth of the bioreactor and the width. The blue color shows you the dissolved oxygen, shows the low dissolved oxygen, and the higher or the red or the green colors are showing you the higher dissolved oxygen concentrations. And you can see clearly that there's a 40% difference between the top and the bottom dissolved oxygen concentrations, which is a big gradient at the same location. And then on the location C, it's not only along the depth, but it's also along the width of the bioreactor, so the diagonal. So almost oxygen gets doubled from going right to the left in the bioreactor. This was confirmed with the CFD simulations, which showed almost similar gradients arising because of the hydrodynamics of the system in the bioreactor. Okay, and this is also not the case only for one type of bioreactor, but this is almost the case for all type of bioreactors. Here you see a very different aeration system. The system we saw earlier was more of a plate diffuser system at the bottom. Here you see the surface aerators, which are at the top. And what you see on the right side is a figure showing oxygen concentrations and ammonium concentrations. You see clearly that there's a higher concentration of oxygen near the top and lower concentrations near the bottom. Whereas in ammonia, eventually, of course, it leads to low concentrations near the top and higher ammonium concentration near the bottom. So it means that it really depends on your system. It really depends on your operations. How are you really operating your bioreactors? We have also done some off-gas measurements to further confirm this. Our colleague, Dr. Giacomo Bolandi, has actually done the measurement campaigns in two different plants in Italy, one in Florence and one at home. And in both conditions, what we did was we put gas hoods across the length of the bioreactor and also along the width of the bioreactor to see is it only along the length when the reaction is really happening along the length of the reactor, or is also the case when it comes to the width of the bioreactor. So normally what you would expect is that, okay, your influent is coming in from left and going to the right, and it's like continuously causing a reaction, and you would not expect a lot of variation between the radial or along the width of the bioreactor. But what we observed in both the cases was that there was always a difference between location 1 and 2, or location 3 and 4, location 5 or 6 in both the cases. And for example, in the case of Rome, there was like almost 20% difference between the oxygen efficiency of location 7 and 8. Which just tells you that there are actually differences when it comes to dissolved oxygen, or actually similar, the other variables as well will eventually have variations in the system. Okay, so this makes things a bit more tricky, because what does it tell you? That, okay, where should we be placing our sensors? And once you have put your sensors in a certain location, how would you interpret it? Are you putting your sensor in a very good location where you expect a value or a measurement which is representative of the whole system? Or if not, then how would you interpret it? How would you derive these conclusions out of your measurements? But what is more certain is that every bioreactor has gradients. We got to know how we can quantify the gradients, how we can measure the impact of those gradients on the performance of the bioreactor. And it actually varies from one plant to the other. It also varies how much flow is coming in, how much aeration you are putting in. So it's really plant dependent feature of a bioreactor. Okay, so one of the solutions is actually, you can look at the mixing, which is about the hydrodynamics, which is about how efficiently you are mixing your system. But how can you really quantify that is only by actually connecting it with the biological performance. And that's what we'll try to do in the CFD biokinetic model.
Usman, before we go to this part, we can actually devote some time to questions, because some questions came in.
Sure.
So Anna, can you maybe read this question? You're still on mute, Anna. Classical.
Yeah, thanks, Swim. The first question is, what about N2O from secondary settlers? Is there any evidence of this? And we've answered, yes, there are certainly studies that have proven that there is a small amount of N2O production in settlers, in secondary settlers. So And the second question is N2O really 3,000 times more potent than CO2? And the answer to that is no, it's only 300 times, but that's still quite substantial. So those are the two questions that have come in so far.
Yeah, and there was one question I have also seen, Anna, and maybe I will go to Giacomo. Which type of sensors did you use in these Italian plants?
Okay.
Yeah, that's a good question. So in the Italian plants, we used for N2O in the liquid the unison sensors. For the N2O in the gas phase, we use our own equipment. The measurement of N2O was an infrared at the end. So we had some gas treatment at the beginning. So it's a long chain of gas treatment before the actual measurement can take place. And then, yeah, dissolved oxygen sensors and the usual ammonia or line signals from and COD from the plant.
Okay. Perfect. Yeah, we have other questions. We will definitely come back to some of them. So, Usman, you can continue with part 3.
Yeah. Okay. Thank you. So maybe I will start with just a little introduction to the CFD modeling. So can you go to this next slide? So computational fluid dynamics is actually what does it do is actually modeling a technique which is based on the real physics. The equations which are used are the real physics behind the flow, and there are normally no trial and error methods. So these are like the true equations based on which we do the simulations. So you always start with either an existing or even a non-existing system, even a hypothetical system, and you transform that into a digital or a computer-aided design of your system, of your bioreactor, for example. We then transform this into very small volumes, which we call a mesh, where we solve all the equations. And based on that, we solve it, we model it, and you get a nice output, which is normally in 3D, which means that you could see it along the width, along the depth, and in any dimension, and which is a function of your variables. But the real power of such a tool comes when you actually run different scenarios, what-if scenarios, which is actually very important given we want to figure out what is the best mitigation strategy for N2O. And you can run multiple scenarios. For example, you can change your aerator configuration and see what happens. So you get a new input, and you can compare it, and you can make an assessment which is the better design amongst all the what-if scenarios. So this is like a basic understanding of how CFD works. But what we do actually now is that to really get to the depths of the problem, which is the N2O emissions, we add kinetics into it. So kinetics is actually coming from these IWA scientific reports, which are very famous or very much used in the industry. Activated sludge models, ESM1, and etc. We combine them with the CFD, and then we try to predict the concentrations. And in the figure you see actually is a treatment facility where there were very high nitrates coming into the system, and there was actually a small mixer at the bottom, which was completely short-circuiting the whole nitrate stream towards the outlet. You would not be able to see that if you would only purely do the CFD modeling. You would see, okay, there are streams coming, but how much is it? How bad is it? You want to know that. By using CFD and kinetics together, you can understand the impact of your design on the performance of your biological system, and then you can run scenarios by moving your impeller or your mixer somewhere else and see if it actually improves your system or not. Okay, so that was me. I think now it goes to Ingmar.
Yeah, thank you, Usman. So what else can we then learn from these CFD models coupled with kinetics? So we have already seen that you can basically estimate local concentrations of all the state variables that are in the ASM models. And that allows you to evaluate your effluent quality, but also to evaluate energy optimization. For example, if you play with the airflow rate, you can run different scenarios. But as Wim already pointed out, there's a lot of criteria. It's really a multi-criteria problem. which means that now when we add N2O and the mechanisms of N2O on top of this, if that is the primary objective, basically you will also get an insight in the other, both in the energy optimization and the effluent quality, and also be sure that this is maintained. So it's like killing 3 birds with 1 stone. And moreover, it also is kind of an X-ray of your 3D X-ray of your system, basically turning it from a black box into a more gray box model, and seeing really what is happening under the surface. Now, a little bit on N2O kinetics, not the idea to go into too much detail. Obviously, they are not present in the traditional ASM models that have been published earlier in the STR that was mentioned. But basically, model extensions have been developed over the last decades. And have been putting in pathways and have been calibrated typically at lab scale. And so what we did is we actually took the most important pathways of these model extensions and actually added it to the biokinetic model, so both in terms of stoichiometry and process rates. And that basically allows you then now to make local predictions of all the relevant species that have an impact on the generation of N2O and also of the N2O concentration itself. And yeah, if new kinetics would be further developed, they can easily be added, just like adding more mechanisms and species in a Guyer matrix as we are typically familiar with. One thing that I would like to stress is that you should also mind not over parameterizing your model. So you can add a lot of mechanisms, but at some point, yeah, if you have limited data available, it's very difficult to calibrate those models. Okay, let's go to another poll here. I will quickly introduce this system. So this is actually a reactor where the inlet is on the bottom left and the outlet is at the top right. And first you have an anoxic zone with baffles, and the arrows indicate how the liquid is moving. And then the final part of the reactor is an aerobic zone. Okay, and so the poll question is, where would you actually start measuring? So would you measure at the start of the anoxic zone, at the end of the anoxic zone, or in the aerobic zone? Would you have a preference where you would on how you would design your measurement campaign? Yeah, so you also have the option all of these locations, or I have no idea. That's also a fair answer, of course. Okay, let's have a look at the results. Okay, so yeah, okay, so the winner is all of these locations. That's obviously always, let's say, conservative or a safe option, because then you will get to know everything. But then, yeah, interesting. The others, like the aerobic zone is also quite popular, and then at the end of the denied zone. Okay, interesting. So let's then continue and actually also give a little bit an insight in what actually comes out of this model. So here you can see the N2O production rate in the different zones. So we are now looking at the top view of the reactor. So it's like a horizontal slice. And left is the anoxic zone and right is the aerobic zone. The base case is a base case with a certain airflow rate. And here what we can see is that actually in the anoxic zone there's not too much going on with respect to N2O production. In the aerobic zone, it's also fairly limited, and it's actually at the end of the anoxic zone where we observe quite a bit of N2O production. And the reason actually for that, you cannot see it from here, is because actually there's a backflow of oxygen from the aeration zone into the anoxic zone. Okay, so clearly a design issue that is causing this. In the middle row, middle figure, you can actually see that now it's a different scenario where actually the airflow rate has been increased in the aerobic zone. So you can see that actually this further emphasizes or increases the N2O production in this anoxic zone. And the lower figure is again at the same airflow rate, but now at a different load, also illustrating that the load has also an impact on the N2O production. Okay, and then from these simulations, you can have the observations of not only the N2O, which I discussed now, but also you can see when you, for example, reduce the aeration rate, what the impact is on, for example, the effluent ammonia, to keep an eye on that, and for example, also on the nitrate concentration. Okay, and you can see that that they can be very different in terms of N2O production, even if your effluent is not really affected by the changes that you have made. Okay, and this is another example again from the Eindhoven case. So here you see 3 measurement points, so 1, 2, and 3 indicated on both figures. And the difference between the top and the bottom figure is, again, the same simulation, but with a different influent load. So meaning that if you look at the figure on the right, we are just looking at 2 different instances of the same day. So it's actually a loading cycle that comes in. And then from the measurements that you see there, you see a certain sequence with respect to the amount of N2O that is produced at different locations. And you also see that that differs throughout the day. And actually, if you look at the colors in the figures, you can also actually tell that the predictions that are being made are qualitatively in conjunction with what we have observed, including also the fact that the red zone, where you have the largest production, actually moves inside the tank, this volume that is indicated there, and that basically it becomes quite cumbersome to keep an eye on that. So the next slide, I think, brings us to the third key point. So the CFD with the integrated kinetic model, including the N2O kinetics, is a powerful assessment tool. So you can actually observe or evaluate where in your reactor and to what extent certain N2O is concentration is being produced. And it could also help you or point in the direction where you have to look for mitigation strategies. Okay, so the CFD biokinetics visualizes actually the concentrations in 3D as a function of the plant design and the operational conditions. It's, as I said, kind of an X-ray from your system.
Perfect, Ingmar. Before we go to this part, I would like to give some more time to questions. So Anna, can you go over a couple of questions, please?
Sure, Wim. First question, what sensors did you use?
The sensors, yeah, that was the one you already read, Anna. So I think it's the gradients question is a very important, very good one.
Yeah. Measurement campaigns should be long-term, I believe. That's what one participant said.
Maybe Giacomo, that is something from you, right? The long-term perspective of measurement campaigns.
Yes, yeah, no, indeed, that's one of the main points of the measurement campaigns. From many studies, we've been learning the long-term feature of full-scale measurement campaign needs to be there. Cannot measure once or in one spot. So both the spatial and the time distribution should be like should cover a long window because of the plant dynamics, because of changes in the influent characteristics, because of changes in the plant operation, but also changes in some design aspects like mixer location, etc. can also be influenced. The long term can indeed be helped substantially with CFD because we can explore different influent fluctuations. That's the important part. You can already see where your gradients will be moving with influent dynamics.
Okay. Yeah, so adding the flexibility, yeah, you mean with the simulations, yeah. So Anna, are there other questions? I think there are many, but we can take a next
Yeah,
one.
there are many questions. Next question, has AM team done any work to compare dissolved oxygen and ammonia gradients in warm versus extreme cold conditions in bioreactors, and how do they compare?
Oh, okay. Yeah, Usman, you're the expert here.
Yeah. Yeah, I've also seen similar questions around varying different concentrations, for example, or different temperatures. One question was also about different MLSS concentration by taking into account settling. The thing is that with the CFD model, you can actually include a lot of variability, a lot of variations inside your model. So we have, I think, not per se done exactly the warm and the cold comparison. But what we have done is different loads, different flow rates, different MLSS concentrations, different aeration rates. So a lot, but these are the things which you can very easily incorporate in your CFD model because it has that degree of freedom inherently in it. So these things can easily be. So what you normally have to do to include temperature is to just have a correlation with your growth rates of the temperature, and based on that, you can just perfectly embed that in. Yeah.
Okay, perfect. Anna, the third question maybe?
This one I think is for Giacomo. Are sludge settling characteristics and gradients in sludge concentrations taken into account in the CFD biokinetics?
Oh, the characteristics of sludge is the question. Yeah, that can be taken into account. So rheology is in fact an important aspect in this picture, and especially in compartments of the reactors, such as the anoxic compartments, in which there is no the active mixing of aeration. You might have zones which we call dead zones, or potentially restagnant zones, which experience higher concentration. So this can be reproduced.
Okay, great. We will definitely come back to more questions, but we can go to this part more, and at the end we have a lot of time for additional discussions. So please keep asking your questions. We will try to group them and then come back to them. Our team will look into them. All right, let's go to the solutions part, because you have seen some colorful drawings. Let's say we have talked about the high-level perspective, but what can we do about this? Let's come back to the main questions, the big objectives, the assessment and the mitigation. Right? I will not repeat these questions, but I'm pretty sure you still remember them. Yeah? It's about prioritization, interpretation of data, and then which measures can you take? Well, if we talk about the assessment stage, and many utilities worldwide are currently doing that because it's important. You want to map the flux or the mass of N2O in your plant under various conditions. Well, many people are now engaging in measurement campaigns, and definitely there, if you look at this, probably this tool can help a lot on helping where to measure, how long to measure, where should you put the sensor and things like that. For example, this is an example from San Colombano in Italy, a plant which our colleague Giacomo knows very well. And these people actually measured with 5 sensors in this zone here. But in fact, what you can see on the simulation, the hotspots are in a different spot. And as Ingmar has shown, these zones also shift. So it's not that this zone always has low N2O emission. It can shift. The thing is, if you have some experience with N2O, 2 years or 3 years of measurement experience, you might start seeing patterns there and you might start avoiding such things. But here's the thing, internationally, so many utilities have to start with measurement campaigns. The question is, should we really go through this trial and error based measurement campaigns? We can definitely do them very smart. So this is one point I wanted to address here. In this specific plant, this is again the top view, had to do with local concentrations and local turbulences, local mixing conditions, causing the pattern. Again, we will not go into detail, but it's very plant specific what happens. Okay, so this is the sensor location. A second part of assessment is, if you are measuring, how do you process your data and which learnings do you extract from your data? typically what has been done is you have a couple of sensors in the liquids phase, for example, at 1 or 2 locations. The people from Unisense are in this webinar as well. And you put them in your plant at various locations, and probably what you are going to do is correlate these measurements with other measurements you have from your plant, dissolved oxygen, ammonia, and maybe other measurements. But what happens typically is you get this data. This is typical plant data of nitrates, of the 2 N2O sensors in this case, ammonia, DO as function of time in your plant. There are a lot of fluctuations. There are a lot of wastewater people here, so we should not explain its dynamic. But look at the locations of these sensors. So one N2O sensor was here, the second one was here. Your DO sensor to control your plant going to the SCADA system is here. And your ammonia sensor is elsewhere, and here they have a nitrate sensor. The thing is, it's very tricky. I think if you have seen these gradients and the simulations and the local conditions, it's very tricky to start correlating this data and make sense out of it. We have seen in the question of Ingmar that extrapolation to within the same plant to other conditions or extrapolations to other plants, that's a very, very big challenge. That was the biggest challenge in this poll. And this has a lot to do with it. So it's not that the measurements are not valuable, but it's very helpful if you know what's going on. So that's the assessment part, sensor location, data interpretation. If we go to the second part, the mitigation part, of course, CFD, as we have shown, is a tool that allows what-if testing, right? It's something you cannot do with any measurement. You have actually a model of your plant, and the benefit of a model is you can start playing with it. You can start testing measures. And then you can quantify how the N2O flux in your plant is in the 3D space. For example, kilograms per cubic meters per day of emission. These are typical curves we use. These are called Riemann-Nobens curves. And CFD is nice, it looks colorful, but in the end, as practitioners, as design engineers, we want to compare scenarios. And it's not so easy based on these colorful figures. What is best, what is worst? So then you have one plot and you put these N2O fluxes on one curve and you can do comparisons. So this is, for example, the fraction of a certain bioreactor volume with a certain N2O production rate. For example, this scenario 1, Ingmar has shown this green curve. Well, 10% of this reactor space, 10% has a flux higher than 20, while the other plants do not have any zones with 20 kilograms or grams per cubic meters per day. Yeah, so this is a way to how to quantify it, varying operational conditions and design conditions. Yeah, so that's the mitigation part. So yeah, what can we do? Because that's also a big debate. Many countries are building experience. We have seen that people in Denmark are, of course, very active. In the Netherlands, there is a big focus on that. UK, Australia, and many other countries are focusing on it. This is the same figure again with the 4 drivers of N2O. Well, many people, a very popular one is to look into aeration, maybe to lower the DO set points. But of course, you will only do that if you don't compromise effluent quality. That's an important one. So here the question again is, if we do something about the aeration, what is the impact on the mixing? Because aeration is also mixing. And what is the impact on my effluent quality? So it's not that straightforward. On the other hand, if you're retrofitting, for example, you can do design optimizations, but in many plants, it's not easy. Or you can test other strategies, for example, alternative aeration strategies. With Air Liquide, we are now starting up 2 projects to test and compare pure oxygen versus just the regular aeration in plants when it comes to N2O. And mixing, of course, is a big topic. We have seen that over and over again. Switching on, off mixers, moving a mixer has a huge, huge impact, often underestimated. The bottom line is, what we see here, it's all about minimizing the N2O production volume. So we look at N2O in a 3D perspective and see it as a big red cloud or several clouds that shift across the plant as function of your operation. And you really have to minimize that volume. So by managing transition zones, oxic, anoxic, avoiding these extreme conditions and maintaining the performance when peak loads come in. If you look a bit in the literature, our colleague Usman, for example, is doing that regularly. You have certain actions you can take. It's moderate DO levels, not too high, not too low. But yeah, of course, it's not so easy in a full-scale plant. What is not too high, what is not too low. People are playing with SRTs, so the solids retention time, COD N ratios optimal, so definitely not too low, and adequate mixing in nitrification and denitrification zones, because in both N2O can be produced, and also the transition zones between them. So what we typically do is we work in steps, and one of the core purposes of this webinar was also to show that this tool is a practical engineering tool. Many people from the past experiences, like 10 years ago, think CFD is not really a practical engineering tool. The thing is, nowadays computers are very strong. We have applied this model, I think, at around 100 plants. This CFD biokinetic model, it's really a routine exercise, and you can really have first valuable results after 2 or 3 weeks in such a project, and it includes intermediate meetings and things like that. We typically apply the Pareto principle. The question is, again, do you really have to test or simulate every condition in your plant? Maybe you should start simulating the 20% of conditions that cover 80% of the time. And that will already give you a very, very good analysis, because that's phase one, the assessment of your current plants. Yeah. Of course, along that, we also can help combining with the measurements, with the data processing and interpretation, going alongside measurement campaigns. Because don't get us wrong, the claim is not to skip measurement campaigns. We just want to provide additional insights with an additional tool to do them smarter, and to also make more sense out of the data that is more generic for your future work. So these are all things we can help with in the assessment phase, and we already run multiple projects at the international scale on that. Then, of course, that's the most interesting part. When you have the model, you can start testing mitigation strategies. This is not impossible. This is not possible with measurements. For example, what if the flow rate changes? What if we reposition some mixers? It's based on this hotspot analysis that, of course, plant specifically, you will have some mitigation strategies. So it's all about what are the measures that would work. That's identification, and then you select them, and then you can test them structurally, and you don't have to always do it on site, trial and error based, because that's not easy at full scale plants. And then when you finally implement, of course, mitigation strategies, many utilities will still start measuring, of course, because you want to see the real impact of your N2O emission. Still then the model is there because new insights come, it's on standby, and we can still run additional simulations to help that further. So this is a bit how we break it up. And the thing is, it can really start small, such things, and then you gradually build up because it's plant specific. Okay. Yeah, before we go to the conclusions, I'm not sure if there are any questions left, Anna.
Yes, we have 2 more questions left to answer live. One is for Usman. It goes, I've had experience of blending CFD and kinetic models in the past. For example, predicting denitrification in FSTs. My experience was that the runtime for these simulations was very significant, and costs prevented us from extracting much value, i.e. running any more than just a handful of scenarios. Is this still the case? Usman.
I think if you look at now the technology, the computer power, which is now readily available, the supercomputers, you don't even need like a supercomputer to run such a simulation. What I'm talking about here is that a pure CFD simulation have like, let's say, six equations or 5 equations at best. And then on top of that, you add, depending on which model you're using, for example, for N2O, you will have like around 15 to 17 extra equations. But we don't see like a significant time requirement for computational increment because of the extra equations, just because you have much more powerful computers and CPUs now. And especially with this GPU accelerated simulations can go much faster.
Yeah, Usman, ballpark wise, it's like half an hour, 1 hour for
no, it's like a few hours. It's few hours, 6 to 8 hours. If we really talk about N2O models, yeah. A steady state N2O model simulation takes 6 to 8 hours on, let's say, 16 core CPU.
Mm-hmm. That's a full scale bioreactor then, right?
Yeah.
Anna, are there
Thank you,
other
Usman.
questions?
Yes, next question is for Giacomo. Can you talk about the N2O model itself and of the CFD N2O? Which one is it and what of all pathways does it represent?
Oh, okay, thanks. That's an interesting question indeed, because we've seen it in the past webinars shared from IWA, from Unisense. We had probably most of the attendees follow those ones as well, and we've seen that the like nice schematics of the main pathways like AOB identification, heterotrophic actions, and hydroxylamine pathways. Now, what we can say in a nutshell today, we didn't want to focus on the detailed pathways, but what we can say is that the main pathways of production and consumption, and even stripping, can be included, so that the main production pathways mechanistically are included in the CFD biokinetics. Then the consumption as well, and the stripping is can also be included with considering the bubble size and the physical relation with the gas-liquid equilibrium.
Thank you, Giacomo. I think that's all for the live questions.
Okay, Anna, thanks. So
Thank
yeah,
you.
at the end of the webinar, of course, we have more time for questions. So let them come. I would say just release all your thoughts on the Q&A, and our colleagues will filter them out. Good. Conclusions. Yeah, we come back to the key points a bit. We see many utilities struggling with really how catching this beast. Let's say how to make sense out of it, and then what to do about it. It's rather complex. And that makes it hard to assess and effectively mitigate, right? So that was the first key point, these spatial factors, these gradients. The key point 2 was, where do you locate your sensors? But also, not only that, on the data interpretation part, it really impacted a lot by the gradients, which are often unknown. When we talk to practitioners, what we see is typically people, of course, expect gradients in a system. In the narration zone, everybody expects that the DO at the bottom of a reactor is lower than at the top because the bubbles had more time traveling up. Everybody also expects that the gradients longitudinal, so with the flow, are different. Well, of course, we have anoxic zones, and your influence is being transformed, right, or decays. But the thing is, not many people, what is a big surprise, they don't expect these huge gradients from one side to another or in other directions. And that's quite an eye-opener. And it's really driving a lot of the N2O pathways. So, and the third key point is, we think with this tool, we can really enable smarter assessment combined with measurements, or even for plants that still are in an assessment or preparing for it. You can already start without any measurements to have some basic insights. And it shouldn't take very long. So that's also a key message. A few weeks and you have the very valuable results. And the second thing, if you have a model, a computer model is a playing tool, so you can test mitigation strategies, which you really cannot test with measurements or other assessments. So that's a bit the summary here. In the end, we really wanted to open the white box a bit of this problem to help practitioners worldwide. So definitely in the coming weeks and months, we will share a lot of more case studies and results, and we will definitely set up a new webinar. So this brings us to the end of the webinar. It's 4 p.m. exactly. So this is, very good. We kept within the time, but we will not close it here. We will still have 5 to 10 minutes more time for questions. If you decide to leave now, please fill in the questionnaire at the end of the webinar. So if you close it, a link or a Google form will pop up. Please share your thoughts, give us some feedback on the webinar, and also highlight the points for future webinars. What are the things that really resonated with you, and what are the thoughts you would like to learn more on? With this, for the people leaving, I would really thank you a lot for attending. There are still a huge amount of people right now in the webinar, which is a very good sign. It was not too boring. But still, let's go back to the question. So Anna, I will come back to you. Maybe you can bring up some more interesting ones.
Thank you, Wim. Yes, I can bring up, there are a lot of questions here. One for Giacomo is, does your model consider N2O stripping in the aerated zone?
Okay. Yeah. I think so. As we mentioned in one of the previous questions, the stripping can be considered indeed together with the bubble size and at need, depending on the objective of the question. Also the coalescence and breakage can even be included there. The equilibrium of gas liquid, it's indeed in there, and the stripping as a consequence.
Thank you, Giacomo.
I can add to that, Anna, that in the first stage we focused on the production rate. For us, that's very important. Really, a production flux that tells a lot about the risk. And indeed, like Giacomo said, then the next step is what we are now doing is with the stripping, of course. But production rates to us, like rates, kilograms per day per cubic meters, it's so powerful. Yeah. Okay.
Okay, next question for Ingmar, I think. Do you think it would be possible to create digital twins of a wastewater treatment plant in order to assist in the mitigation with dynamic datas?
Yeah, that's a very interesting question, and I think we didn't really stress that, but I think a powerful part of setting up such a model is it would be a shame if you would set it up just once and not reuse it. So indeed, digital twins is something that where you can again reuse the knowledge that you have gathered from these models. And the typical approach that we use is to create compartmental models from this. So this was also something that Usman did in his PhD for first time, and we are applying it even more. So here you have an example of that. So instead of having the very detailed CFD simulation, you really focus on the most important features of your mixing issues and heterogeneities that you have, and then you can combine that with let's say a traditional model with the N2O model, and that could allow you, it would be much faster, and then that could be run in a dynamic way. So that's I would think that that's probably the step that comes after this. But yeah, very good question.
Yeah, and combined with that, it brings us a bit to other questions, like on gradients. For example, there are a lot of questions on also how do you model biofilm processes or alternative processes? For example, granular activated sludge, MBBRs, other types of processes. It comes down to exactly the same thing. How do you describe the mixing? And then indeed, how do you update your model to account for these things? But it's really key, and there are methodologies for that. It's very detailed, but we can definitely discuss these things in separate calls with you if you have specific cases. So Anna, yeah, I will not take your time all the time.
No worries. Another question for Usman. So you mentioned steady state. Does this mean that CFD is a snapshot? And what about N2O dynamics? Can you do dynamic simulations to see how N2O changes in a reactor over time?
Yeah, indeed. So the transient simulations or the dynamic simulations are perfectly possible. But what we need to see, as Wim also mentioned, that's the Pareto factor. So by doing the 20% work, you actually get the 80% picture of your system. And what we have done in the past is, and what we see is pretty much sufficient. And also very practical and pragmatic is doing the snapshots at different moments. So not running one simulation and saying that this is the representative, but rather taking multiple snapshots across the time and seeing and assessing the dynamics and the impact of dynamics on the performance. So in that case, it's like few hours of a simulation, and you can run multiple scenarios with varying conditions.
Thank you, Usman. Another question for Wim, I think. Side stream treatment reactors are often pinpointed as a significant N2O source, often ignoring the high nitrogen load they process. Did you already do modeling of this type of reactor?
Yeah, great question. Interesting one. So, for example, we can talk about NMOX processes. That's a typical one for side stream treatments. Various types of these processes exist, of course. We have indeed heard from a couple of people that they produce quite some N2O, but it makes sense. Maybe proportionally not more per kilogram of nitrogen that comes in than an activated sludge process. But the thing is, the load is so massive of nitrogen that you have this high production rate. Combined, of course, yes, with the low DO levels they operate at. And that makes it extra tricky. It makes it extra relevant to also optimize the mixing in these systems. The question now is, did we include such kinetics? Well, we definitely have codes there that we, for example, for NMOX, to model that and to adjust our model for these kinetics. So that's definitely possible. And we have been thinking about it a lot, about this topic. So that's a very relevant one. Combined with that also, we see a drastically increasing interest from industry. So industrial wastewater treatments. Some of these industrial wastewater treatment streams have so much nitrogen. The plants are very big. And also there, we expect so much N2O emissions. The matrix can be so different than a municipal plant. Very similar, I would say. Side streams, industrial wastewater, definitely interesting to look into.
Thanks, Wim. Another question for you is, are you able to model what is happening inside a biofilter or any biofilm system regarding N2O?
Yeah, so I will start answering the question and then I might give it to Usman. But so that was something I related to already. Yeah, the point is your biomass is, let's say, more distributed. It's not like everywhere diffused like flocks. So it's more concentrated, and where it is, of course, the rates of conversion of your wastewater, the rates of nitrification, denitrification locally are way higher, right? So definitely there are ways to include those local conditions, and then I will give it to Usman and make my life very easy.
Yeah. Well, these are already included, the variations in the biomass considerations, and also depends. Sometimes, I mean. And in some plants where you know that the biomass availability is quite a lot, and then you can consider this a reduction in degree of freedom, and you can keep constant, for example. So that's the power of a model. It's very much possible to tailor it to a certain situation, and that we do all the time because it saves time, it saves resources.
Yeah. Exactly. We are more and more modeling MBBRs now. MBBRs, so these carrier systems, moving bed biofilm reactors. There you of course see that the gradients in your carriers can be very big. Depending on the mix, you can have zones with a huge amount of these carriers, and then the vertical, horizontal, and the gradients in other directions are drastic. But yes, there are ways to include that. It's a process intensification, which means everything is faster, and gradients are more drastic.
Thank you, Wim and Usman. I think this is the last question. Is it possible to scale up the emissions from pilot scale to full scale level using CFD modeling?
Yeah, scale up. That's one of the applications that is most dominant when we look at CFD biokinetics. We have used it so many times to help scaling up MBRs, MBBRs, other technologies that are new. And we really see a huge scalability because Usman also mentioned it's physics-based, and that's a bit the benefit of CFD. The physics scale along with the treatment plants. So the thing is, we have in many cases started modeling at the pilot scale with customers, and then we scaled up virtually. We call it virtual piloting, virtual scale up to a full scale system, and we simulate, like we create, let's say 5, 6, 10 different candidates full-scale designs, and one of them is the best, and this is typically what our clients then build with very, very good outcomes. We have several of them being built operational today, and it's really working. Usman, I don't know if you want to add something to that, the scaling.
Oh, that's correct. That's correct. Again, the power of CFD is that you can virtually test anything, any scale, any situation, any condition, any variation in the system.
Yeah,
with a reasonable accuracy. Yeah.
Yeah, when it comes to scale up, typically we see people doing piloting, and a scale up exercise is difficult. We see them doing piloting for two reasons. The first one is to figure out what is the best design. The second one is to gain operational experience. For example, is this sensor falling? What is the falling of my memory? Whatever. So a lot of operational aspects. The first one, the design aspect, according to us, you should really not spend piloting money on that. Let CFD do the job. Test virtual design improvements, inlet locations, even a baffle size, or they can make a huge difference. And that makes it very valuable